Good morning to all of you. In previous session, we have seen different types of filters. There is analog filter, digital filter, then active filters, passive filter. Then we have seen depending on the operational frequency, they can be categorized at low pass, high pass, band stop, and all pass filters. As well as we discussed about various advantages and disadvantages of filters. In today's session, we will be discussing our filter designing by approximation of derivatives method. So this method is also referred as backward difference of derivatives method. So our filters can be designed by using approximation of derivatives. So our filter design by approximation of derivatives. So this method is used to convert the given analog filter and IR analog filter into digital filter. So this method is also referred as backward difference for the derivatives. Backward difference for the derivatives. So we'll also see some examples in today's session how to obtain the digital filter using. So we'll look at some examples where we'll be converting the given analog filter into digital filter by using approximation of derivatives, or which is also referred as backward difference for the derivatives method. So for this conversion, the will be provided with the analog system function. So this analog system function is denoted as h of s, and we need to convert this h of s into the digital system function, which is denoted as h of z. So we'll try to convert this h of s into h of z by using these methods, right? So in today's session, we'll be using approximation of derivatives method to convert the analog system function into the digital system function. So for this conversion, the mapping formula uh, used the mapping formula for the backward difference for the derivatives is given as small s is equals to 1 minus z inverse upon capital T. Okay, so this mapping formula will be using for converting the given analog system or analog filter into the digital filter by converting its analog filters system function into digital filters system function. Okay, so we'll be converting h of s into h of z. Okay, so let's look at the example how to convert this analog filter to the digital filter. So in this example, we have to convert the given analog low pass filter with system function h of s using the backward difference for the derivative method. Okay, so the given analog filter system function is capital H of s is equals to 1 upon s plus 2. Okay, so for converting it into digital filter, use the mapping function for the backward difference for the derivative. Okay, so what is this mapping function is? So mapping function is s is equals to 1 minus z inverse upon capital T. Okay, so we'll solve this equation for s is equals to 1 minus z inverse upon capital T. Okay, so the system function for the digital filter is, it will be h of z, which will be obtained from h of s by substituting s is equals to 1 minus z inverse upon capital T in the given equation. So 1 upon, in place of s, will be substituting 1 minus z inverse upon capital T plus 2 will be as it is. Okay, so if you simplify it, so you will get h of z is equals to, if I am simply solving this equation, so it will be capital T upon 1 minus z inverse plus 2t, right? So this will be h of z. Okay, and when the value of capital T is not specified in the example, then you can assume capital T is equals to, once again, that is nothing but the sampling period. Okay, so assume here capital T is equals to 1 second. So therefore h of z is equals to, if I am substituting 1 second in this case in place of capital T, so it will be 1 upon, this will be 1 minus z inverse plus 2 will be there, 2 plus 1 will be 3, so it will be 3 minus z inverse. Okay, so this is nothing but the required digital filters system function. Okay, so this is how you will be solving this problem where you want to convert the analog filter into digital filter by using the backward difference for the derivative method. Let's see another example. So again, the solution is very simple in this example as well. Okay, again you have to use backward difference for derivative to convert the analog filter with system function h of s into digital filter. Okay, so the given system function for analog filter is h of s is equals to 1 upon s square plus 16, right? By using backward difference of derivative, that is s is equals to 1 minus z inverse upon capital T, right? The system function for digital filter is, it will be h of z, which will be obtained from h of s by substituting s is equals to 1 minus z inverse upon capital T. Okay, so we'll have 1 upon, in bracket, 1 minus z inverse upon capital T square plus 16. So if you simplify it, so h of z will be, if you take the square of it, okay, so t square will be in numerator, right, all upon, if you take the square of it, so 1 minus 2z inverse plus z to the power minus 2 will be there, right, and this 16t square will be there, right? So 1 minus 2z inverse plus z to the power minus 2 plus 16t square. Okay, so this is the required system function for the digital filter. Again, capital T value is not specified in the example, so we'll assume capital T is equals to 1 second. So h of z will equals to 1 upon, if I'm substituting t is equals to 1, so it will be 1 plus 16, so it will be 17. It will be 17 minus 2z inverse plus z to the power minus 2. Okay, so this is nothing but the required system function for the digital filter. Okay, so this is how you will be converting analog filter into digital filter by using approximation of the derivatives or backward difference for the derivatives. Let's see one more example. So here again you will be using same method. Okay, so given system function for analog filter is this one. You will be using s is equals to 1 minus z inverse upon capital T as a mapping function. For obtaining h of z, you will be solving h of s for s is equals to 1 minus z inverse upon capital T. So if I'm substituting this value in this equation, so I will have 1 minus z inverse upon capital T plus 0.1 whole square plus 9. Okay, so if you simplify this equation, so you will get h of z is equals to, if I'm taking the square of this equation, so t square will be there. Okay, so t square I will sending in numerator, right? And by performing this addition, and this t square will get multiplied with this 9 here, right? So if I'm trying to solve this equation, so I can specify here, I'll write h of z is equals to t square all upon this z to the power minus 2 will be there, right? So it will be z to the power minus 2 minus this 1 minus z inverse will be there, this 0.1 t will be there, right, in multiplication of z inverse. So I'll just write down the simplified equation here. So it would be 2 in bracket 1 plus 0.1 capital T z inverse plus 1 plus 0.02 t plus 9.01 t square will be the equation. Okay, so just what I had done, I have simply taken the all terms closer to each other. Okay, so z raised to power minus 2, there is only one term. Z inverse, there are two terms, so I have taken those terms nearer to each other, and the remaining constant terms are here, right? So again, if you try to simplify it, so you can substitute capital T is equals to 1 second in the given equation, and you can identify what will the final equation for this simplified system function. Okay, so again you can assume capital T is equals to 1 second, you can substitute in this equation, and you can find out the final value of h of z, right? So this is how you will be identifying the uh, digital filter system function from the given analog filters system function. So this process is called as what? Designing of IR filter by using approximation of derivatives or backward difference for the derivatives. Okay, so method is simple. You will be provided with the system function h of s, okay, of analog filter, and you have to obtain the system function for the digital filter, that is nothing but h of z, by simply using this mapping function s is equals to 1 minus z inverse upon capital T. If t is explicitly specified in the example, then you can substitute that value in this case. Otherwise you will assume capital T as 1 second. Okay, so in next session we'll be looking at the IR filter design by impulse invariant method. So thank you for joining this session.